welcome. We are going to do basically several stages of this talk, and at each of the situations where we show pictures, where we have a context switch or so, just feel free to shout some questions, because we want to have it a bit more interactive. So this is about pypy, new Python implementation that we have been working on for 3 years now. One of the talkers, actually, Rigo, is not here. He's one of the initiators, also together with Christian, who's sitting here. He couldn't come. He was basically very exhausted. We had a lot of work in the last month, actually, to get a lot of things, also releases and EU reports and all kinds of stuff finalized. And so he's basically now in Switzerland in the mountains skiing and relaxing a bit. Okay, so let's first talk a bit about how many of you actually know Python or have been programming in Python a bit. Okay, and how many know what a virtual machine is, how it works? Okay, that's about half, so that's good to know. So Python is actually a virtual machine architecture. It has a parser and a compiler, which takes a source code program, transforms it into bytecode, and then you have a virtual machine looking at the bytecode and interpreting, just like the JVM, the Java virtual machine does it, interpreting these bytecodes and executing all kinds of operations, and actually to make your program work the way you want it to be. It's a strong, dynamically typed language. I think the Dylan people yesterday and some other people mentioned this already. There's always some kind of confusion. It is so that unlike something like BASIC or Visual Basic or whatever, it does have strong types. So you have an integer, you have a string. It's not automatically converted into an integer or something. It's really an integer, and you get type errors if you try to do something that you cannot do with strings if you want to treat it as a number. So it's dynamically typed in the sense that you don't have to statically declare all the time what the type of each variable is. And it has a rather clean object model at various levels, especially also the C level. It's about a 10-year-old language, but even if you look today at the C code, how the virtual machine is implemented in CPython, it's really rather readable C code. And that's kind of like a very good thing that you can at all levels basically understand and relate the various concepts to each other. Okay, so next one. So what Python implementations do we have today? Today, there are a lot more experiments and things going on, but these are like currently the main implementations. We have CPython, which is the thing that everybody refers to as Python. And we have Jython, which is compiling a Python source code to Java bytecode. So it directly executes on the Java virtual machine. It integrates quite totally with Java. So you can subclass Java classes. It's actually, I think, in one recent survey, Jython was the #1 scripting language for Java, considered to be used by like 60% of the people who want to use a scripting language within Java. Then we have recently actually the one guy that came up with the idea of Jython, compiling Python source code to the Java virtual machine, is Jim Hugunin. And he was bought by Microsoft a year ago about. And so he joined the Microsoft Research Lab and is now heading the Iron Python effort, which is basically verifying the .NET 2.0 architecture and the facilities regarding dynamic languages. So there he's doing something similar. He's compiling Python programs to the Common Language Runtime, which is the CLR abbreviation there. And then there's pypy, which evolved in the last 2-3 years. And that's a self-contained and self-translating Python version that is implemented in Python itself. We're going to get into more details there. So these are the 4 main implementations at the moment. And it's interesting to note, that's a common feature in the Python community, I would say, that these 4 projects, even though Microsoft is involved and even though you have a grassroots effort Python implementation, they are cooperating. They're really like, this year we sat together and thought about what can we share, how can we work together. So on the developer level, at least, there is collaboration. On commercial levels or other levels, it might be different. So then, what is it regarding pypy? Well, first, some facts about it. Started in 2002. The aims were formulated by, basically, at that time, by Christian, Armin, and me, where we invited people for a first sprint in Germany. And a sprint is a 1-week meeting. And we sat together and basically had various aims at what we wanted to do, what we wanted a project like this to be like. And what we wanted to have is a Python implementation that is for research purposes, but also for performance reasons. It's like a project that reinvents a bit the whole language implementation. And the aims are flexibility and being able to try new concepts at the language implementation level and speed at some point. We were doing that from the beginning with test-driven development. And we, in 2003, basically, we arranged for EU funding because we had grown we had like met several times and decided that if we actually want to do such a project, completely re-implementing the language and then translating it to like down to the processor level, that we really need to work somewhat more full-time on it than meeting every 2 months for 1 week. That just wasn't enough. So we went for that, and there's a whole talk about this tomorrow, how that actually worked out and the community aspects. And currently, just to have a few numbers there, we have like 350 subscribers to the development list. We have around 150,000 lines of code that we wrote, and you're going to see what it all contains. It's quite a lot. And we have around, I think, 20,000 visitors per month on the website. The whole thing is MIT licensed. That means that everybody, each of the participating parties is free to also commercially use it and redistribute it in any way. Okay, so the method, like I mentioned, is test-driven, sprints. It's very much driven by the open source culture. A lot of the developers come from there, have done other projects that have influences on the project we are doing, and that's going to be talked about tomorrow. So the main thing to understand about the implementation is that we do implement the whole language interpreter within Python itself. And obviously, if we just were standing there and wouldn't do anything else, then we have a problem because we cannot really get out of ourselves. We would basically depend on ourselves, which doesn't really work. And so we basically started by using CPython and implemented pypy on top of that and have like a completely correct language implementation. But then we need to do something more. And what we do there is we translate it into lower level languages. In order to be able to do that, it's a dynamic language. It is strongly typed, but there's no type declarations whatsoever. So what we have to do, and that's a major second part of the talk, is we have to infer all the types in the program in order to be able to then translate it to machine-level code, basically. That also means that major parts of our implementation are implemented in some kind of static subset of Python. That what we call restricted Python. It has a lot of, you can basically do lots of things, but what you cannot do is you cannot violate certain staticness conditions. It's not a formally defined approach. It's more like a balance between being able to type infer and not using too dynamic things. But what is very important, and that's a distinguishing feature compared to other similar approaches, is that when you actually start up the interpreter, the pypy interpreter, you can use any Python feature, completely dynamic. You are not restricted at all. And then you have to reach a certain point where your whole program that is in memory is in some kind of static state. All the functions, everything, they have these staticness conditions. So only at that point do you need to be in RPython. So you will find lots of source code in pypy that is completely dynamic. It's using, well, some of you know it, it's using exec statements, dynamically constructs functions, all kinds of stuff. It doesn't matter, because we are not translating source code. We are really working from the program in memory and take this snapshot and translate from there. The architecture, that is the something that we basically came up with in 2002, and the basic architecture is really quite unmodified, and that's not really a surprise, because some of the people taking part were very experienced in the CPython implementation and having done extensions and even a just-in-time compiler. That's the one guy that is not here at the moment, Armin Rigo, did a just-in-time compiler for CPython, implemented in C, very hard stuff. So from the beginning, we had an architecture that was proven to really work quite nicely, and that is, we have the parser and compiler producing the bytecode. We have the bytecode interpreter, basically very similar to how CPython does it. It's completely compatible. Then we have something what we call the object space. You can consider it something like an object library and implements all the operations you can possibly do on integers, on strings, and all this, all the basic types that you need. And the virtual machine basically is comprised of this bytecode interpreter and the standard object space. And then, of course, we also need, because Python is a practical language, there's lots of modules, and in order to be useful, we actually have to have a certain number of built-in modules so that you can do some I/O and printing. Okay, so to visualize this a bit, we have a user Python program, just an arbitrary Python program, that gets into the parser and compiler. That is also completely implemented in Python. Then we produce bytecode, and that is then interpreted by the bytecode interpreter. And actually, can you scale down one? It'll... Oh, okay. Oh, no, it does. Okay, a bit more? No. Okay, what you would see here is that's the scaling thing of the beamer, I guess. What you would see here is that the bytecode interpreter dispatches operations on the object space. So it does not really, when it looks at the bytecodes, it shuffles objects around, but actually to implement integer addition and all this, it just calls this object library, object space thing, and this does it. And that is a very useful abstraction to have that is not present in the other Python implementations. And that is also something that the Perl 6 people are looking into now, and we get to that. So next one. Okay, now you have to scale up a bit. So a few words about the parser and compiler. It takes Python source code, turns it into an abstract syntax tree, which is some kind of structure that represents in an abstract way the whole syntax of the language. Then it takes this abstract syntax tree and generates code objects or bytecode. It works, our parser implementation works from the normal CPython grammar definition, a bit tweaked, I think, but basically the same. And I think at the recent meeting, beginning of December, we managed to actually make it modifiable at runtime. So you can actually change the syntax at runtime. At the moment, you can only remove syntax, but it's also possible to add syntax. Like the print statement always sucked, so we just got rid of that. And I think what is interesting maybe is seeing an interactive command line example, how what it actually means if you have something like code objects in Python. And let's just look at one function. This is a function we're going to use throughout the presentation. It means that you build the sum. It's very simple. You build the sum over a sequence. You start off with a 0 total counter. You go with an index. It's a bit C-like here. You go with an index over the range of until the length of the sequence. So the length of the sequence is something like whatever you pass in as a sequence. And the range builds a list. And this I basically traverses then 0, 1, 2, 3, 4 until the length of the list. And then you sum up, you say the total, which starts at 0, is added with each sequence number. So you basically build the sum of each of the elements in the list. And you return the total. So if you now, you can import the dis module